Okay, so I'll be talking about the round complexity of secure quantum computation. This is joint work with Andrea, Dakshita, and Fermi. So it turns out that quantum information is pretty useful for cryptography. And probably the most famous example of this is information theoretic key exchange, but there are many other examples, including quantum money, so unclonable currency, other types of unclonable cryptography, so like encryption or signature schemes with unclonable keys, for example. Provable deletion of information, copy protection of programs, and the list goes on, and I'm probably missing many citations, but the point is that quantum information can be used to perform like various tasks that are completely impossible with only classical information, okay? So, one could imagine a world in which quantum information is being leveraged to perform all of these interesting tasks. Now, one prominent goal of classical crypto has been, one goal has been to distribute trust among multiple parties, right? In order to avoid like single points of failure or corruption, things like this. So a pretty natural question to ask is whether these cryptographic tasks that make inherent use of quantum information can be securely distributed among multiple parties, okay? As a concrete example, maybe you have a quantum money scheme, and where, of course, the banknote generation procedure is, of course, quantum, but now you might want to distribute this generation procedure so there isn't a single entity that is just able to generate banknotes, right? But okay, so this is just one way to motivate a more general task that is the focus of this work, which is secure multi-party quantum computation, okay? So what is this? It's, same as the classical, well-studied classical MPC, except that we're going to allow parties to have quantum computers and quantum inputs. And their goal is now to compute some quantum functionality over their quantum inputs to produce some quantum output in its most general form, right? And here actually we could consider like these inputs and outputs also being entangled, okay? So to do this, of course, they'll communicate with each other now over quantum channels, right? And security is the same as classically. We're going to say that if an adversary is corrupting some set of parties, say 2 and 3, they shouldn't learn anything about the honest party inputs, except for what is already implied by their output, okay? And so, of course, like classical MPC is extremely well studied and is, dates all the way back almost to the beginning of modern crypto. Multi-party quantum computation has also been studied, but of course, not as much. So what is known is that, there are these two works in the early 2000s that constructed information theoretically secure protocols in the honest majority setting, okay? Later on, the dishonest majority setting was considered. And these works, DNS, DGJMS, they present basically compilers showing that if you have secure classical computation, you can construct secure quantum computation, even against malicious adversaries corrupting an arbitrary subset of the parties. Okay, and so this is, these works really are works establishing the feasibility of secure multi-party quantum computation, right? And so this is kind of the state of affairs prior to our work. So, one potential issue or drawback with these protocols really is they're extremely interactive, highly interactive protocols, right? So, in particular, like the number of rounds of communication required, and keep in mind this communication is in general going to be quantum communication, so these parties, sending quantum states to each other, right? In general, in these protocols, it grows with the depth of the quantum circuit, okay? And so, round complexity is a notion that's been heavily studied in the classical setting. And our work, the starting point of our work, our focus is on round efficient secure quantum computation, okay? So we know these feasibility results exist. Okay, so now we want to study whether we can really obtain round efficiency in the quantum setting, right? And to be clear about the particular setting that we are interested in is this dishonest majority setting, where adversary can corrupt an arbitrary subset of parties and can act arbitrarily and maliciously during the protocol. Okay, and we're also going to assume some minimal trusted setup. So pretty common model of assuming like a common random string that the parties have access to. Okay. Right. So this is the focus of this work. We have various results both in the two-party and more than two-party or multi-party setting, and I'll kind of split this talk into those two parts. I'll be able to like give all our result statements along with some a little bit about like the techniques we use to get them, but we'll leave a lot of the details to the paper. Okay. So to begin with the two-party case, we'll first look at what's known about classical two-party computation. Okay, so these results date back to Yao in the 80s, who show that if you assume a two-message oblivious transfer protocol, and oblivious transfer is a extremely simple two-party functionality, right, where we have a receiver with a bit B, sender with two strings, and the receiver at the end of the protocol learns one of the two sender strings, right? So this very simple oblivious transfer functionality that if you can do this in just two messages, then kind of amazingly, you can compute any arbitrary classical functionality over two private inputs, XA and XB, delivering output to A, right? So basically OT, the simple functionality, implies the ability to do secure computation of arbitrary functionalities, and even in a round preserving way. Okay, and so sometimes this is called NISC, this protocol, a non-interactive secure computation protocol. And kind of the malicious version, like NISC with malicious security, was formalized by this work in IPS. Okay. So our first result is just going to be a quantum analog of this, right? We're going to show that how to construct a quantum NISC protocol. In other words, assuming just the same assumption. So, well, of course, now post-quantum. So assuming post-quantum two-message oblivious transfer, we can construct a two-message protocol for computing any functionality, any quantum functionality that delivers output to one party. Okay, so quantum NISC. And I can say a few words about how we construct this protocol. And to do that, we'll need a little bit of background on classical garbled circuits, right? So a classical garbled circuit basically consists of two procedures, garble and eval. And garble takes as input a circuit or a functionality f and an input x, and produces a garbled circuit f tilde and a garbled input x tilde. Okay, and the evaluation functionality takes this garbled information and produces from it the output f of x. Okay, and security intuitively states that like this garbled information kind of only contains information about f of x, and this is formalized by saying there's a simulator that just given f of x but not x, right, can produce something that is indistinguishable from this garbled information. Okay, and this is it's only non-trivial when garble is simpler or lower complexity in some sense than f. Otherwise, garble could just evaluate f already, right? But when garble is sufficiently simple or efficient, then this object has many applications. Right. So this is a classical garbled circuit. You could ask for the same thing in the quantum setting, right? And there's probably many ways to formalize or like kind of specify what sort of properties you'd want out of a quantum garbled circuit. And I will discuss one particular set of properties. So, here, let's say you have, say, a classical description of a unitary U, but in general, maybe a more general quantum operation as well. And you have a quantum input x, right? So what we want out of our garble procedure is going to be, the procedure that garbles U and produces U tilde, we're going to require is going to be completely classical. Okay, so takes a classical description of U and outputs a classical description of U tilde. And moreover, the procedure that takes the input X and produces a garbled input X should be simple in some sense, which I'll be more specific about later. But this particular set of properties out of a garbled circuit, was considered in this recent work of Rakersky and Yuan. And they sketched how you might construct this, and then we go and formalize and prove security of it in our work. And to be clear about what I meant by simple, basically the input garbling procedure just basically takes your input X, appends some 0 states and some so-called magic T states, and then re-randomizes everything with a random Clifford. And this is simple because basically this Clifford computation is in general simpler than an arbitrary quantum operation. Okay. Right. So we're going to take this object as our starting point, a quantum garbling procedure down here with a classical unitary or classical circuit garbling subroutine, right? And we're going to use it to build the NISC. Okay, so recall we have a 2 quantum parties, each with their quantum input, and we want A to recover its output YA at the end of the interaction. Okay, so first we're going to have A send over an encrypted version of its quantum input. For this, we'll use something called an Clifford encoding. And then we'll just basically have B send back a garbled input. Okay, so it's going to append its input XB to A's input XA, and it's going to garble that input by appending 0 and T states, re-randomizing with the Clifford, right? So this gives A the garbled input. We also have to give A the garbled unitary, right? And so we're going to enable this with a classical 2PC or a classical NISC protocol, okay? And this is possible because this procedure that garbles U into U tilde is completely classical, okay? So we can kind of run this under a classical 2PC, and this is very helpful because we're going to get some malicious security out of our malicious secure classical MPC. So we're going to basically be able to ensure that U tilde is computed properly, okay? So so A gets this garbled input, gets this properly computed U tilde, and from that is able to obtain its output. So this is the basic idea. There's still kind of one big issue that needs to be taken care of. This classical 2PC is ensuring that U tilde is correctly computed, but what about this garbled input? Okay. So, in particular, a malicious party B might send a malformed garbled input, right? In particular, they might be lying about, or they might not send proper 0 and T states. So without going into details, we're going to need to include some extra 2-message protocols that basically allow A to check for these properly formed 0 and T states. Okay. And these checks are inspired by similar checks that were used in DGJMS in a more interactive setting, and we basically show 2-message versions of these checks. Okay. So yeah, this gives a picture of basically how our quantum NISC protocol is constructed. And before moving on, I will mention we have a corollary of this, is that we can use this to build a particular type of a designated verifier, a non-interactive zero-knowledge protocol for QMA. And it has interesting properties like reusable malicious security. And the actual statement we get is that if we combine 2-message oblivious transfer with MDV NISC for NP, then we get this protocol for QMA. Okay, and this is the same. This MDV NISC for QMA is the same object. It was also constructed by Schmelly, also appearing at this crypto conference. One difference, kind of the advantage of our protocol is that the prover in our protocol only requires 1 copy of the quantum witness state. Okay, whereas in this other protocol from Schmelly, there's the prover needed multiple copies. Okay, so this is just one application we have of our quantum NISC. Okay. So good. Now I'd like to move on and say, well, so far we've just considered protocols where one party obtains an output, right? So what if we want, the more general setting where both parties are obtaining some output, and what if we, furthermore, we want to maintain the optimal round complexity of 2, right? So there's a pretty natural classical approach to doing this. So if you have some, classical functionality now that has 2 outputs, you can basically consider writing it as 2 separate functionalities. One that just outputs like A as part of the output, and the other that just outputs B as part of the output. And then you could consider running 2 NISC protocols in parallel. Okay, so you could have, the blue NISC that's delivering A's output and the orange NISC that is delivering B's output. This is a natural approach, and it can be made to work in the classical setting. However, there are some significant barriers to making this work in the quantum setting. Okay, and the reason, one reason is that this seems to require cloning inputs, right? You need to run these 2 parallel protocols on the same set of inputs. But if your inputs are quantum, you can't in general clone them, right? And kind of even worse, this, like, say that this functionality is randomized. Well, what you're actually doing when you write it as 2 functionalities is kind of fixing a particular random string, R, and then using that same random string in both of these, like FA and FB, right? Because if you didn't do this, then these outputs, YA, YB, wouldn't be properly jointly distributed, okay? So this relies on the fact that you can really take a randomized protocol and make it deterministic by fixing the random string. And this is something also that you just cannot do in the quantum setting, right? Because maybe randomness is coming from measurement, okay? And so this issue, the fact that you can't kind of like fix the randomness and split up the protocol like this is, it even comes up even if these inputs, XA and XB, are classical, but maybe the parties want to compute a quantum functionality over them. Okay, so these are kind of, no cloning and not being able to fix the randomness are two issues that kind of prevent this natural approach from working. Okay, so this is just to highlight maybe some difficulties in getting a 2-round protocol. And now I won't be able to go into details about like our technical contributions here, but I'll be able to give result statements. So basically, the first thing we do is we relax the problem a little bit, and we construct a 2-round protocol where pre-processing is allowed, meaning that the parties can exchange some messages beforehand before they obtain their inputs. Okay, and then once they obtain their inputs, it's just a 2-round protocol. And so we can construct this object from sub-exponentially secure LWE. Okay, so 2-round, 2-party quantum computation with pre-processing. Of course, we are also interested in what's actually happening in the setting without pre-processing. Like can we actually obtain a truly 2-round protocol, right? And here it's still like pretty open. Okay, we only have like a partial negative result and a partial positive result. Okay, so our partial negative result is really in an attempt to formalize this intuition I was mentioning before about what makes this problem difficult. And this formalization takes the form of saying, well, there is a particular like class of simulators, right? That is impossible in the sense that you can't construct a 2-round protocol with what we call an oblivious simulator. And an oblivious simulator is basically one that kind of programs the CRS independently of which of the 2 parties is corrupted. And this is kind of interesting, or I should say, well, we only obtain this results under an information theoretic conjecture. Okay, but this is interesting because this type of oblivious simulation does suffice for classical 2-round 2PC. Okay, so it kind of shows under this conjecture a separation between the classical and quantum cases. But we have a partial positive result as well that says that, well, if you assume access to a quantum oracle, in other words, like basically assuming like ideal obfuscation of particular quantum functionality, then you can construct a 2-round 2-party computation protocol, and this necessarily uses non-oblivious simulation. But I call it, I'd say this is a proof of concept because we don't even know any heuristic approaches to constructing, obfuscation of quantum circuits, right? So this is kind of, at this point, it's not even a heuristic construction. It's just a proof of concept saying how, maybe suggesting how one might construct such a protocol. Okay, so again, yeah, we have these partial positive and negative results, but this question is remaining open. So I think that's all I wanted to say about the two-party case. I can quickly say something about what we do in the multi-party case. And really, I'm just going to be focusing on one particular issue that comes up in the multi-party case, okay? Which is that now we have to be worried about the number of rounds. Like in the end, we want a constant round protocol, right? So we do not want this number of rounds to depend on the number of parties partaking in the protocol, right? And to see why this might be difficult, generally in MPC, you have to have, each party is going to first commit to some input that's going to be used in the computation, okay? And the classical setting, every party can classically commit to their classical input and then broadcast their commitment to all other parties, right? In a single round. But broadcasting quantum information is not possible, again, due to no cloning, okay? So let's look at basically how prior work, so DGJMS, how this work approaches this input commitment phase. So here you have your quantum parties, and say you want your first party to commit to their input x1. What's going to happen is each of the parties chooses their own uniform randomness in the form of a Clifford. And party 1 is going to send a Clifford encoding to party 2 of their input, and then party 2 is going to kind of re-randomize this with their own Clifford, and this is going to continue all the way around the circle of parties. And at the end, what we end up with is party 1 holds this encoded quantum state, but the parties all share the encoding key. Okay, so grounding key is kind of secret shared among all the parties. And this is a good enough commitment to allow MPC. So the issue with this is that the number of rounds really grows with the number of parties, right? You're sending this quantum state around in a circle. So our approach to round collapse this step is to use teleportation, okay? So in the first round, we'll have parties set up EPR pairs with each other, okay? And then what we're going to do is have the parties, teleport and apply their random Cliffords simultaneously, in a single round, right? And this basically leads to the same result as before, except that there are teleportation errors now inserted between all of these Cliffords. But this is okay because we can then use classical MPC again in a round efficient way to correct these teleportation errors. So this whole input commitment phase can be done in a constant number of rounds. Okay, and so this is kind of the one issue I wanted to highlight, and in the paper, we leverage this and combine with other techniques to eventually arrive at a full-fledged constant round multi-party quantum computation protocol. In particular, assuming 2-message OT, we get a 5-round MPQC protocol. And then we also have the same sort of result as in the 2-party case. We can do even just 2 rounds as long as we allow some input-independent pre-processing. And this result, again, follows from sub-exponentially secure LWE. So this is our result statements in the multi-party setting. So now, yeah, I just wanted to quickly recap. So basically, what this work is an initiation of the study of round efficiency in multi-party quantum computation. And there's another, there's a concurrent work also appearing at this crypto conference that also studies round efficiency. Okay. And I wanted to also remind you of there's basically a few interesting challenges that arise that are specific to the quantum setting when you want to attempt to kind of come up with round efficient protocols. Things like functionalities cannot be made deterministic, which is quite useful in the classical setting. Inputs can't be cloned. Quantum information can't be broadcast. And so these are useful things in the classical setting, and we need different techniques in the quantum setting to obtain kind of similar results, right? And then finally, this open question that I think is pretty interesting is like, does two-rounder, like round optimal secure computation exist, right? We have these two kind of partial results, and like kind of this partial negative result that I hope is kind of just eventually going to point to basically new methods for obtaining eventually a positive result. But this question is remaining open. So yeah, that's all I wanted to say. So thank you for listening.